what is variation of sines? I think I say it wrong. Variation in sines of a polynomial px. That's the number of variations in sines for polynomial px is the number of times the sign changes from positive to negative or negative to positive on the coefficients of px. Yeah, assuming that px already in descending order. Okay, now suppose, for example, if I have px equals to 3x to the 4th minus 5x cubed plus 7x squared plus the 4x plus 9. Okay, notice that it's already in descending order. Then the number of variation in signs of this polynomial will be one time here. Notice that from positive 3 becomes negative 5. As positive becomes negative, so that's one time change. Okay, and from negative 5 to positive 7, that's another one time change. From positive 7 to positive 4, no change of sign, no change of sign. So this polynomial px has two variation of sign, variation in signs. Okay, the sign changes from positive becomes negative and then becomes positive again. Still positive and still positive. Okay, now that's what it means to be variation in signs. Now, what the Carter's rule of sign says. The Carter's rule of sign consists of two parts. We'll focus on the first part first. The first part says the following. The first part says that let px be a polynomial with real coefficients. So the coefficients has to be real numbers. It's okay to be irrational as long as they are real coefficients. Then and the number of positive roots you can say that's the same to number of X-intercepts counting multiplicity is equal to the number of variation in signs of px or less than that by or less than that by an even number. So we will look at the number of variation in signs, for the px. That will be equal to the number of positive roots, the number of x-intercepts on the right-hand side of the y-axis, okay? And or less than that by an even number. In our earlier example, we have, I have hard time to see my pointer. Okay, in our earlier example here, we see that px has two variations in signs, right? So according to Descartes' rule of sign, the first part, then px has two positive zeros or zero positive zero. There are two variations of signs. In this first example, there are two variations in signs, right? That's why we have either two positive zeros, or if you subtract that 2 by an even number 2, then you have no positive zero. But for sure, there will not be only one positive zero. There will not be three positive zeros. How many zeros is polynomial supposed to have?
4.
4. Why?
The degree of the polynomial.
Because the degree is 4. That's right. Now then, Descartes' rule of signs actually break it up even further. Then if there are 4 zeros, how many of them positive? And later on, part B will tell us how many of them should be negative. Okay. Now the number of positive zeros is equal to the number of variation in signs, or less than that by an even number. Okay. Now, how about part B, the second part? The second part is very, very similar. Then the number of negative roots so basically you can say that's also your the number of x-intercepts counting multiplicity is equal to the number of variation in signs of p negative x, or less than that by an even number.
Sorry, quick question. What's the even number part for?
Do you remember conjugate zero theorem?
Yes.
Yeah, so basically, if you have a complex zero, like the root or the solution of an equation is a complex number,
Yes.
then the conjugate also a solution, right? So basically, if any root becomes a complex solutions, they must go in pair.
Yes.
Right. So
right.
then if if the number of positive roots should decrease and become complex roots, then they must decrease by 2 or 4 or 8.
Oh, so because of the conjugate root theorem, that's why it's
yeah. So let's say suppose that we suspect that a polynomial has 5 positive zeros, right? Because
yes.
of the number of variations is 5, let's say.
Mhm.
Then imagine if any of these 5 zeros turns out to be complex.
Oh, I see.
Now, if it turns out to be complex, then it cannot be 4.
Yeah.
Cannot, because what? If they go to
3.
complex, then they need to go in pairs, right?
Yeah.
Okay, so either 3 or 1, like that.
Okay. Yeah.
Okay?
Yeah. Thank you.
Mm-hmm. Now, let's apply this part B here using the example we have earlier. We have this px, maybe I use this color. We have this px. Let's do it here. So what is p negative x? Now, p negative x, basically replacing x by negative x, right? Let me simplify. That's 3x to the 4 plus 5x cubed plus 7x squared minus 4x plus 9. Now notice that the positive coefficients are these, and the negative coefficient is this one. So how many times the sign changes? 1 and 2, right? So that px has, from here, then we say px has 2 or 0 negative zeros. Okay, let me ask you to copy that down, and then we will start working on problems. The idea of this Descartes' rule of sign is actually quite simple. It doesn't really help us to find the zeros, but it tells us how many zeros should be on the right-hand side, how many zeros should be on the left-hand side, and it helps a lot in telling us when to stop. Okay, now let me screenshot this. Let's do some problem. So I will get this problem. Let's say we have this problem. I quote this from I don't know where. Where's that from? Fall 15. That's from fall 15 math 26 at SMC test 2. So we have this polynomial fx equals to blah 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 blah. Now part A. Use the Descartes' rule of signs to find the possible number of positive real zeros. Positive real zeros. So using that polynomial, see how many times the sign changes. 1 time, 2 times, 3 times. Right? So how many positive zeros the polynomial is supposed to have?
3 or 1.
3 or 1 positive zero. Okay. Now this polynomial have 5 zeros, right? This polynomial has 5 zeros. So far, before this part A, we don't know how many positive, how many negative, if any, okay? But once we apply the Descartes' rule sign, we know we need to look for at most 3 positive zeros. If we do guessing game later on, when we start doing guessing, once we get 3 positive zeros, we stop. Then we move to finding negative zeros, okay? Now, how about part B? Use the Descartes' rule signs to find the possible number of negative real zeros. Now, to find the negative zeros, I need to first see what will negative f negative x look like. So negative x to the 5th minus 12 negative x cubed plus 2 negative x squared plus 27 times negative x minus 18. This will be negative x to the 5th plus 12x cubed plus 2x squared minus 27x minus 18. Now, if you do this enough number of times, you will see some phenomena that if you replace x by negative x in a polynomial, then only the odd exponent will change sign. Only odd exponent will change sign. You see that? Only odd exponent will change sign. The one with even exponent will stay the same sign.
Can you repeat the phenomena? What was that statement?
Yeah, if you replace the x by negative x,
Okay.
okay, then only the odd exponent will change the sign.
Okay, thank you.
Yeah. Well, think about it. If the exponent is even and you replace x by negative x, the negative to the even power stay the same sign, right?
Yeah.
Right. Okay. Basically, if I write it up here just for identification, x to the 4th, when I replace the x by negative x, I take it to the 4th power, there will still be x to the 4th, right? Because what, the exponent is even, right? But if you have odd exponent, let's say x to the 7th, then when you replace x by negative x, then we change the sign. Right? Positive here, it's positive here becomes negative. Okay? Well, anyway, then go back here. Then how many times the sign changes in this f negative x? 1, 2, oh, only 2, huh? Okay, so there will be 2
Or 0.
or 0, negative 0. Okay, now in other words, later on, if we found, let's say later on we find 1 negative zeros, then we need to look for another one. We cannot stop at 1. We need to look for 2 negative zeros. Okay, now let's go to part C. Use rational zero theorems to determine the possible rational zeros of this polynomial fx. C is equal to plus minus. Rational zero theorem says if a polynomial with integer coefficients, that's what we have there, the coefficients are integers, then if the 0 is a rational number, then it must be a factor of the constant. In this case are 1, 2, 3, 6, 9, 18. Is it right? That's the factors of 18. Over the factor of the leading coefficient. What's the leading coefficient?
-1.
Hmm?
1.
fx. Just one, right? Yeah, actually, doesn't matter positive or negative. Yeah, it doesn't matter positive or negative. But then I need to list them. There will be plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus 9, plus minus 18. Okay, now in part D, find the zeros of this polynomial using the candidates you get in part C. Now, we will do trial and error, but if we do trial and error, we need to know what candidate to try to test. And of course, from here you see that you don't try 4, you don't try 5, you don't try 8, you don't try 20. However much you like those numbers, you don't. Okay, now let's see. The polynomial fx is, let me write it down here. That's x to the 5th minus 12x cubed plus 2x squared plus 27x minus 18. Okay, let me ask you to find what is f1. You can use syntactic division, of course, but if you think about it, when you try to find f1, you basically replace all the x's by 1. Is it right? So you will only add the coefficients. And here, when you add the coefficients, it happens to be 0. Now, that implies 1 is a 0. Is it okay? That implies 1 is a 0. Because 1 is a 0, I can use that 1 to reduce the polynomial. 1, 0, negative 12, 2, 27, negative 18. I know 1 is a 0 from here. From here, I know that 1 is a 0. So I know this part here will be 0. Okay, that's not the issue. The issue is I would like to know what is this here. I would like to know what is this here. Okay, if I know those numbers, that will be the coefficient of the other factor of this polynomial fx. Let's say I bring that 1 down. This is 1, this is 1, this is 1, negative 11, negative 11, negative 9, negative 9, 18, 18, 0. So for now, we have fx is equal to, now because 1 is a 0, then factor by factor theorem, x minus 1 is a 0. X to the 4 plus x cubed minus 11x squared minus 9x plus 18. Are you with me? So I know that in the, because when I plug in f1, when I plug in 1 into the polynomial, I get equals to 0. Then 1 is a 0. Because 1 is a 0, I use that x minus 1 to divide, and reducing the polynomial, I factor x minus 1 out. The remaining polynomial, which is also a factor, is now degree of 4. Now, in fact, if you think about that further, notice that when we add the polynomials here, 1 plus 1 plus negative 11 plus negative 9 plus 18, this one here, when you add the coefficients, 1 plus 1 minus 11 minus 9 plus 18, what's that?
0.
That's still 0, right? Now, which means I can do that 1 is another 0. I continue from there. 1, it must be another 0. You see, right? So now I have x minus 1 squared times x cubed plus 2x squared minus 9x minus 18. Is it okay?
How does that trick work again?
What trick work?
There's a little trick that you just did.
What trick?
You were saying that you can use 1 again just because the coefficients added up to 0.
Yeah, yeah, the coefficient of this green highlight here, if you add those numbers, that's equals to 0, right?
Yeah.
Yeah, so it means when you plug in x equals to 1, that's 1 is another 0.
Oh, okay, I see.
Okay?
Yeah.
Now, with this 1, 2, negative 9, negative 18, I don't think the sum is 0. So 1 must not be another 0. Okay, but can you guess other number? Can I use 4?
No,
Why not?
it's not on that list.
Yeah, because 4 is not in that list. That's right. Okay. Can you suggest something to try?
9.
9?
Yes.
Okay, let's try. So if I use 9 here, so what I do here is testing, okay? I'm not sure if 9 worked though. 9, so this is 9, 11, 99, 90, this is 810, this is super positive, right? Are you with me?
Yeah.
So is 9 a 0?
No.
No, 9 is not a 0. But there's one more thing to say. There's one more thing to say before I move forward. Even though I know 9 is not a 0, but there's an important result I didn't teach you last time. Now I can insert that. It's the following. If you look back to this negative 18 here, if you look back to this negative 18, according to rational zero theorems, then the candidates are plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus 9, plus minus 18, right? Okay. Now, when I try 9, it doesn't work. Agree?
Yes.
When I try 9, it doesn't work. So 1 doesn't work anymore. 9 doesn't work too. However, from this result, you see that the third column, the third row, the entries are all positive. The entries are all positive. Now, so what if all the entries are positive? It means there is no more 0 to the right of 9. Because the entry here, 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 here are all positive, it means you can eliminate all candidates greater than 9. In other words, while I try to use 9, see if it is 0, it's not a 0. So I kill 9. But because the entry down here are all positive, then I kill positive 18 at the same time. 9 give me all positive coefficients here. Right? Now, if 9 give me all positive numbers on the third row, then any number greater than 9 will not be 0. It's just like instead of finding the solutions, now I find who are not the solutions. And on my way to find that this 9 is not the solution, I also find out that 18 is not. Okay, so 9 is not. Let me erase it. This is the things that you're supposed to show on the scratch paper though. Now, if you then find the zeros, like what I did up here for these 2 ones there, then you write it on the test paper. But the 9, you try it on the scratch paper. If it doesn't work, then you don't need to show that part. Let me tell you, I believe 3 will work. Don't ask me why. I just guess. Actually, you saw earlier that when we try 9 doesn't work, right? And therefore positive 18 will not work. Let me try 3. Okay, let me try 3. 1, 3, 5, 15, 6, 18, 0. Oh, so 3 is a 0. Therefore, 3 also, x minus 3 is a factor, right? In fact, of 5 zeros that I'm supposed to look for, I already find 3 of them. So the remaining polynomial that is not factored yet must be degree of 2. We already get 3 zeros, right? We already get 3 zeros. 1 with multiplicity of 2 and 3. So far we have 3 positive zeros. I use those 3 positive zeros to reduce the degree of 5, becomes now degree of 2. Then, what do I do from here?
You can factor.
Yeah, just factor them. You don't need to use synthetic division anymore. You can, but why you want to work so hard? Right? You can factor it here. Now then, from here you see, oh, the zeros are x equals to 1 with multiplicity of 2, x equals to 3, x equals to negative 2, x equals to negative 3, and they are with multiplicity of 1. Okay, now if you check how many positive zeros, what are the positive zeros? X equals to 1 with multiplicity of 2, x equals to 3 with multiplicity of 1. So how many positive zeros?
2.
3, counting the multiplicity, right? Okay, now notice that it is in line to what we get in part A. In part A, we then now find that we have 3 positive zeros. Okay, and then if I go on looking at the negative zeros, what are the negative zeros? Negative 2 and negative 3, each of the multiplicity of 1. So we have 2 negative zeros, which is in line to our answer in part B. Okay, now once we are able to find all the zeros here, then we can write this in factored form already. So let's say, for example, I continue part what? Part E. Part E, I say write fx in factor form. Then you will say fx equals to x minus 1 squared, x minus 3, x plus 2, x plus 3. Now, then from there, I expect you to be able to answer this question. What is the y-intercept? Look at the polynomial.
18.
The y-intercept is
18.
almost right.
0, 0,
Hmm?
negative 18.
0, comma, negative 18, not positive 18. How about the x-intercepts?
Zeros of the.
Hmm?
There are the zeros of the.
Yeah, but
the,
zeros only numbers.
oh, I'm sorry. 1, 0.
1,
Multiplicity
0,
becomes
3,
0.
zeros, negative 2, zeros, negative 2, 0, and then negative 3, 0. Okay, now suppose then from here I want to graph the function. What the graph will look like. Too much. What the graph will look like. Then 0, negative 18. 0, negative 18, let's say it's here. 1, 0. 3, 0. Negative 2, 0. Negative 3, 0. Okay, what's the far end behavior? You can do sine graph first to help. Yeah, because it's degree of 5 with leading coefficient positive, so the graph must look like starting from negative infinity on the left hand side, and it will go to positive infinity on the right hand side. Okay, a sine graph will help, by the way. Then negative 3 is a 0 with odd multiplicity. In fact, it's multiplicity of 1, so it will cross just like a line. And negative 2, also a 0 with multiplicity of 1, so it will cross just like a line. Go to negative 8. 1 is 0 with multiplicity of, I think that's multiplicity of 2, right? So it will behave like an x squared before then it jumps up here. Okay, so the sketch of the graph is approximately like that. Let me know if you are done copying that. Now, once you are done, let's look at the next question. Let me scroll it up. Let's see this example here. This question comes from the same source, the same test. Fx equals to this polynomial. Part A, easy ones. What's the far end behavior? I'm sorry, the y-intercept, sorry.
24. Positive 0, 24.
0, 24. How about the far end behavior?
A positive infinity on both ends.
Positive infinity on both ends. So positive infinity to positive infinity. Now, how many positive real zeros D has X at most?
2 or 0.
2 or 0, and the reason is it changed one time here, it changed another one time here, right? So it has 2 or no positive zeros. Now, how about how many negative real zeros Px has at most? I think the wording is supposed to be Px has only, not at most. At most 2. But the purpose of the question is actually how many positive real zeros does Px have? Okay, now how about to find the number of negative zeros?
F of negative x.
We need to look for P negative x or F negative x. So P negative x is equal to degree of even degree, I don't change the sign. Odd degree, I change the sign. Let's see how many times the sign change. One time here, another one time here. So there will be 2 or 0 negative zeros. Part D, does Px have any zero between x equals 0 and x equals 3? And to find out, let's try to find what P0 is and what P3 is. P0 is 24. We know it from the Y-intercept. Okay, but how to find P3?
Remainder theorem.
Remainder theorem. And for remainder theorem, we use synthetic division. 25, negative 154, negative 4.4. I put 3 here. 25 times 3, 75. That's 100. This is 300. 146 times 3. Oh, I don't know. It's like 432. 438. 438. This is 434 times 3 will be 12, 0, 1, 2. So this will be 1, 3, 2, 6. 1, 3, 2, 6. Oh, they have the same sign, huh?
Yeah.
So what can we say?
No zeros.
No, we cannot say no zeros. If they have the same sign, we cannot say anything.
Oh,
Intermediate value theorem gives no conclusion.
okay.
No conclusion.
So, Professor, question.
Mm-hmm.
I recall you said you don't like us just plugging in, 3 into the original polynomial, but I found that that'll be like shorter and simpler.
You go ahead. Go ahead if that's what you do.
Okay.
Yeah, go ahead. Yeah, give no conclusion when P0 and P3 have the same sign. Okay, so we don't know if any zero between 0 to 3. However, the reason I asked you this question and the reason I would like you to do synthetic division for P3, notice that on the last row, it's all positive, right? Now, in part E here, let's list the possible rational zeros. It's the factor of 24 over factor of 25. So that will be plus minus a factor of 24. 1, 2, 3, 4, 6, 8, 12, 24. Ugh. And the denominator factor of 25. 1, 5, 25. Right? So that will be, let me list the, I can just do the plus minus, but for now, let me list the positive. That's 1, 2, 3, 4, 6, 8, 12, 24. Okay, and then 1/5, 2/5, 3/5, 4/5, 6/5, 8/5, 12/5, 24/5. You can just actually put the plus minus in front of each one of them if you want. 1 over 25, 2 over 25, 3 over 25, 4 over 25, 6 over 25, 8 over 25, 12 over 25, and 24 over 25. Now, supposed to be with all plus minus, right? Supposed to be each one of them with plus minus. Supposed to be, let me put the plus minus in there. So there are a lot of candidates, huh? And we may get confused of if we do trial and error later on, we don't know which one to do first. Don't you think so? Okay, but notice the sidekick, the sidekick, side effect of what I did in part D. Notice that when I try 3, as in do synthetic deviation against x minus 3, the last column, the last row, all positive numbers. Now then, it's by something called boundedness theorem. By boundedness theorem, if you divide by the C is a positive number and the last row are all positive, then by boundedness theorem, there is no 0 greater than 3. In fact, in this case, including 3. So I can eliminate now. I can eliminate 3, 4, 6, 8, 12, 24, and 24 over 5. Okay, simply because you did this dividing by, you find P3 the way using synthetic division, and you happen to have a clue. You know what? Then there will not be any zeros greater than 3. Okay, that actually eliminates a lot of candidates, though. Let's see. Next one. Let me copy paste again. Next one here. Part F, what is the quotient Qx if Px is divided by x minus 1? If Px divided by x minus 1, Px divided by x minus 1, then I do synthetic division and the number outside will be 1. The coefficients are 25, 25, 25, 25, negative 154, negative 4, 24, negative 4, 24. Let me ask you to do this synthetic division. You do it, I do it too. Twenty-five here, 25, 50, 50, negative 104, negative 104, negative 108, negative 108. So this is negative 84, supposedly. Okay, so Qx, the quotient will be 25x cubed plus 50x squared minus 104x minus 108. That's the quotient. Everybody, are you okay?
Yes.
Okay. Now, but we have something here, something nice to talk about. What is that? Notice that I like to do sidekick, and some students cannot handle me because of that very reason. What kind of sidekick? Okay, let's see. When x equals to 0, when x equals to 0, when x equals to 0, what is the y?
24.
That's positive, right? When x equals to 3, what is the y? Also positive, right? Positive 1326 from part B. When x equals to 1, the value is?
Negative
Negative what?
84.
Negative 84. So you know where to look at that, right? Okay. So part F, my question is, my explicit question is, what's the quotient? What is the polynomial for the quotient? Okay. But implicitly, if you have the side of your eyes, kind of like look at that, hey, you know what? It means P1 is negative number. Now, when you see this structure, then you know that there must be a 0 here, and there must be a 0 here. By intermediate value theorem. Right? There's a 0 between 0 to 1. There's another 0 from 1 to 3. And there's no more 0 after 3. Yeah, there's no more 0 after 3 because we saw in part D, the last row, all positive. Okay? Now that gives us the reason then, okay, suppose I need to find all those 4 zeros. If I need to find all those 4 zeros, what should I try? Then on my scratch paper, what number do you want to try?
1.
1. 1.
1/5.
1/5. Why don't you try 1?
Ugh.
Because implicitly we did, right? It didn't work. Okay? Yeah, implicitly we did. So the 25 here, this becomes 5, this is 30, this is 6, this is negative, what's that? 148. Ooh, ugly. Ooh, ugly. I don't think I want to go on.
No.
No, please don't. Okay, what else?
Twenty-four 25ths.
24 over 25.
Yes.
Okay. (24 over 25), that's 25, this becomes 24, this is 49, nah, ugly. I don't think I want to go on. I mean, it may be, but I don't think I want to go on with that. If I need to go on, I do it later, but it's too early. How about 2 over 25 or 3 over 25 or 4 over 25 or 6 over 25? Let's say 2 over 25. 25 here. That's 2. No, it's not good. Seems like whatever we try doesn't work out. Let's try something greater than 1 then. Between 1 and 2, what do we have? 1 and 3, what do we have? 1 and 3, we have 2. Let's try 2. Does 2 work?
Isn't 4?
Huh? What?
-4.
Oh, -4 here. That's what I did. -4. So this is -8. That's -12. That's -24. That's our 0. Yay! Okay, so I will formally write it here. That's 25, 25, -154, -4, 24. That's 25, 50, 75, 150, -4, -8, -12, -24, 0. Okay, we reduced that to the degree of 3 right now. Let's try to find one more. But see, on my scratch work, I don't need to start from the very beginning anymore, right? I can just start from here now. 25, 75, -4, -12. It seems like it's quite hard for us to find the one between 0 and between 0 and 1. Do you want to try a negative number maybe? let me try -2. Instead of sitting here doing nothing, just keep on thinking, right? Do something. So -2, 25, -50, that's 25, -50, -54, positive 108, this is positive. Okay, so between x equals 0 to x equals to -2, this is positive. Okay, so you see that they have the same sign here. So even though I don't get a 0 using x equals to -2, I get some feeling, you know what, it's both positive here. So if I try to find another 0, I will not pick first any number between -2 and 0. Okay, I will go to the next one. Let me try, let's say -3. I think -3 will work. You want to try?
Okay.
Right? So let me go on. So I will try -3. So right now, my polynomial has become x minus 2, x plus 3, 25x minus 4. That's already degree of 2 on the last one, and actually I can go further. I can factor it further, right? That's 5x plus 2, 5x minus 2. So the zeros are
2,
x equals to 2, x equals to -3, x equals -2/5, x equals +2/5, and all of them with multiplicity of 1. Now then, the next question, I wonder what question is that. That's part G. Part H. Write px in factor form. Write px in linear factor form. Now, linear factor form actually means the following. Linear factor forms actually the following. Polynomial equals to the leading coefficient times x minus something, x minus something, x minus something. Okay. In other words, we don't allow coefficient 5 here. We don't allow that. We'll pull it out. We'll pull it out. Okay, so px equals to the leading coefficient is 25, x minus 2, x plus 3, x plus 2/5, x minus 2/5.
I would say this would be the most standard form of how polynomial should be or look.
Repeat it again.
This linear factor form is the standard form of how a polynomial really exists, like as far as the coefficient at the end for like the rest.
At the front, yeah, the coefficient at the front, and each parenthesis has to be a linear factor.
Mhm.
It must be x plus or x minus something.
Okay.
Yeah, okay. Yeah, and then actually to go a bit further, we are about to graph this though. So what's the Y-intercept, the X-intercept? I think we are aware of all of them. Y-intercept will be 0, 24. The X-intercepts are 2, 0, negative 3, 0, negative 2, 5, 0, 2, 5, 0. Okay, and you can do the sine graph first. Let me go ahead with the sketch of the graph. So 2, 0, 2, 5, 0, negative 2, 5, 0, and 3, 0. Let's say it's here, negative 3, 0, while the Y-intercept is 0, 24. So let's say it's here. Now, then what is the far end behavior?
You said positive infinity on both ends.
Positive infinity on both ends. Oh, I forgot. Last time I supposed to say top instead of infinity. I will call that top here. Basically, I come from the top. Later on, I go to the top. Okay, and because each zeros has a single multiplicity, so when I cross the x-axis, I will cross that linearly. Wow, it's a big roller coaster there. Approximately like this. Okay, I think it is possible that what happened here is supposed to look like this. Maybe, I'm not sure though. Maybe like this instead. Doesn't matter. Okay, so that's the sketch of the graph. That's the sketch of the graph. Now, I'm about to give you a break. When we come back, we will go on with 4.7. And basically, after this, you will take a look on my old tests and try to do some problems from there, especially on the polynomial and, if possible, rational functions too later on. On your screen, you should see problems that you should study from my old tests. This one here. This is the one. Okay, right now it's 5:41. We will come back at 5:50. Okay, let's see what is a rational function. Let I use Rx for rational function. Let Rx be a rational function. Let Rx be rational function. Now, then Rx will be the quotient of two polynomials. And I will denote polynomial on the numerator as px and polynomial on the denominator as qx. But the numerator and denominator are both polynomials. Okay, now furthermore, as for notation, px, I will use a for the coefficients. I will use a for the coefficients and n for the degrees. while Qx, I will use B for the coefficients and M for the degrees. Okay, let's say for example, just to identify the structure, let Rx equals to x squared minus 4 over x squared plus 5x minus 6. Okay, so what is A2?
Zero.
Are you sure?
4, -4.
No.
I don't know.
A is the coefficient for the numerator. Now, A subscript 2 is the coefficient for x squared on the numerator. That's 1.
Okay.
The one here, this is A2. How about A subscript 1?
Now -4.
No.
Now it's 0.
0. Now, -4 is what?
A not. A 0.
A sub 0, that's right. How about B1?
5.
That's 5. Okay, that's just for notation. Now, in this section, we will answer the following question. What are the questions we need to anticipate? Questions to anticipate. The easy one first. Easy. First, the domain. Second, the Y-intercept. And then C, the X-intercept. I think these three are quite easy. Let's just work on this example 1 here. For us to find the domain, X-intercept and Y-intercept, we will first factor it. Okay? At this point, I do not forgive you if you cannot do factoring. That's the rational function. Okay, then from that rational function, what is the domain?
All reals except -6 and 1.
All real number except -6 and +1. Okay, how about the Y-intercept?
Mm. 2/3, -2/3.
Are you sure?
Yeah. I mean, 2/3, 2/3. 0, 2/3.
0,2/3. Okay, now of course, the Y-intercept only exists if 0 is in the domain, right? If 0 is in the domain.
0,2.
Yeah, okay. So actually, in general, you will see the Y-intercept of a rational function will be 0, A sub 0 over B sub 0. Okay, of course, as long as B sub 0 is not equal to 0. Right? Now, how about the X-intercept?
±2.
Almost right.
Is it
2, 0,
0?
-2, 0. Now, you will see that the X-Intercept, basically change the Rx equals to 0, right? Okay, is Px over Qx. Now, a fraction equals to 0 if the numerator is 0. Is that right? Okay, so if you want to find the X-intercepts, all you need to do is see the zeros of the numerator. Okay, now of course you need to check if the zeros of the numerators actually in the domain. In this case, 2 is in the domain, -2 is also in the domain. Is it okay? Okay, let's do another example. Then you can see better what I mean. Another example, example 2, I will use a rational function that looks very, very similar. X squared minus 4 over x squared plus 5x plus 6. Notice that if I factor this, we will get x plus 2, x minus 2, x plus 2, x plus 3, right? Okay, so from there we see the domain is all real numbers except -2 and -3. How about the y-intercept?
-2/3.
That's 0, -2 over 3. How about the x-intercept?
Two.
X-intercepts supposed to be 2, 0 and -2, 0, right? When we look at the numerator. However, 2, -2 is not in the domain. So I have to cross this out. Because -2 is not in the domain. Okay? Now, that's for the domain, y-intercept and x-intercept. It can go out of our way quite fast. So far, the questions that we need to anticipate, the first one is the domain. That's easy part. And then the y-intercept, that's still easy. The x-intercept, that's still easy. Just be aware that it has to be in the domain of the rational function. Now, the next ones, something called horizontal asymptote. And vertical asymptote.
First, I had a question.
Uh-huh.
So when you have like terms in the numerator and the denominator, you don't cross them out.
Not yet, at least not yet. At least
Okay.
not yet. Yeah, we will do that later, but let me mention it later. Okay, let me mention it later. Horizontal asymptote and vertical asymptote, we will discuss this first. Okay, but let's see what is horizontal asymptote, vertical asymptote is. Let me try to graph a function here. Give me a second. I need to first explain what is vertical and horizontal asymptote, right? Okay. Now, I give you this graph here. This is actually the graph of the first example. Now, but first, let's see what is a vertical asymptote, horizontal asymptote. Now, horizontal asymptote is a horizontal line. Horizontal asymptote is a horizontal line that to which the graph of the line will get closer and closer to as the function approaching infinity or negative infinity. Let's take a look here. Now, this line, this green line here is called horizontal asymptote. It is not part of the graph. Okay, it's not part of the graph, but it is the guiding line to which that the function gets closer and closer to as the graph approaching, going to negative infinity far to the left, and when the graph approaching to the right. You see what I mean? Now, that's what we mean by horizontal asymptotes. The graph gets closer and closer to this horizontal line. Oops. The graph gets closer to this horizontal line as x goes to positive or negative infinity. Okay? Now, that's what we mean by horizontal asymptote. You can say y equals to c is a horizontal asymptote if as x approaching infinity, as you go to positive infinity, as we go to positive infinity, the x goes to positive infinity, okay? The graph, the y is actually approaching that value c, the same value c here. Now, in this case, n as x going to negative infinity, as the x going to negative infinity, the y value also approaching the same number. Okay, now that's what we meant by horizontal asymptote. Now, how about vertical asymptote? Now, vertical asymptote are this line here, and this line also. Okay, those are vertical lines to which the graph gets closer and closer to, but not touching. The graph gets closer and closer to, okay, it will escape to infinity or escape to negative infinity as x approaching that number. Okay, so formally, x equals to c is a vertical asymptote if as x approaching c, when we get close to that value, the y value is actually going to positive or negative infinity. Okay, now that's what we meant by vertical asymptote. Now you see in case of fractional function, the graph will never intersect vertical asymptote. Maybe I write it down. In rational function the graph never intersect vertical asymptote. It may intersect horizontal asymptote, but never intersects vertical asymptotes.
So are you talking about how the segment in the middle crosses C, right?
Yes, yes. So you see that we have horizontal asymptote here, right? Okay, and the graph actually intersect horizontal asymptote. For the horizontal asymptote, it is okay that the graph cross it. However, for vertical asymptote, the graph never cross it. It will never cross it. And the reason it will never cross it, as you will see later on, it has something to do with the numbers we need to avoid when we look for the domain. Okay. Now the thing is, after we know what vertical and horizontal asymptotes looks like, let's find out how to find them. For horizontal asymptote, here's the rules. You need to memorize, but at the same time, I think you can memorize this easily if you use some instinct. First one, if the degree on the top is less than the degree at the bottom. If the degree on the top is less than the degree of the bottom, then the horizontal asymptote is given by y equals 0. Let's say, for example, if I have this rational function, let's say if I have x minus 3 over x squared minus 4. Notice that as x goes to infinity, x minus 3 will go to infinity, right? But likewise, x squared minus 4 will also go to infinity. Agree? Now, even though the numerator and denominator both go to infinity, which goes to infinity faster?
The denominator.
The denominator. Why?
There's a degree of 2.
Yeah, degree of 2. Okay. So imagine if you and I actually driving to Las Vegas, okay, and let's say Jeffrey used BMW, and I use my Prius. Both of us will eventually arrive, right? But who do you think will arrive first?
BMW.
Supposedly, right? But supposedly, I mean, I just try to kind of like illustrate that your BMW is a lot faster, and Prius is kind of like, duh, it's so slow. Imagine if I use bicycle instead, right? I will arrive, but by the time I arrive, you're already like winning or losing your life there. Okay. Yeah. So yes, the idea is like both of them goes to infinity, but the higher degree will go to infinity faster. Okay. Now that's the intuitive point of approach. Another approach is as the following. You see that this function actually can be written as the following. I can divide the top by x squared and the bottom by x squared. This is actually a calculus way to show the work. Now then, notice that this becomes 1 over x minus 3 over x squared over 1 minus 4 over x squared. Now then what happens if x goes to infinity? Then on the top left it becomes
0.
becomes 0. How about top right?
I don't know. Also 0.
It is still 0, that's right.
Yeah.
Okay. How about the bottom left?
1.
It becomes 1. How about the bottom right?
0.
Right? Now then when you put them together, okay, so when x goes to infinity, you will get 0. In fact, that's also true if x goes to negative infinity. Right? But then it satisfies the way we define horizontal asymptote up there. When x goes to positive infinity, or when x goes to negative infinity, the y value approaching that number c, and in this case the number c is 0. Okay, so you can remember if the degree on the top is less than the degree at the bottom, then the bottom will go to infinity faster. Eventually the ratio goes to 0. Second.
Yeah. Quick question.
Uh-huh.
So 1 over a very large negative number is 0.
That's right, huh? Yeah.
I didn't know that.
Mm. Yeah. Well, it's you can think of it this way. It's like some number divided by a very big number that becomes 0, right? Okay. Now, how about negative big number? That becomes negative 0. What do you think?
Oh,
Which is 0 anyway,
okay.
right?
Okay.
Mm-hmm. Now then, what happens if the degree is the same? Then the horizontal asymptote will be y equals to leading coefficient on the top over leading coefficient at the bottom. Okay, but you see the degree has to be the same, so this guy should be equal to this. Now, let's see an example. Suppose Rx equals to x squared minus 4 over x squared plus 5x minus 6. According to our theory there, this rational function has numerator degree of 2, denominator also degree of 2. So the horizontal asymptote will be y equals to, the leading coefficient on the top is
1,
1. The leading coefficient at the bottom is
1,
also 1. So the horizontal asymptote is y equals to 1. Okay. In fact, this rational function that we just did has this graph. This is the graph. Okay, this is the graph, and if you trace that horizontal asymptote, y equals to 1, you see that it gets closer and closer. The graph gets closer to and closer to y equals to 1 as we go very far to the right, and also as we go very far to the left. Is it okay? That's the y equals to 1.
You use the same calculus method, or?
If I use the same calculus method, and I will divide by the highest exponent. So Rx equals to x squared over x squared minus 4 over x squared over x squared over x squared plus 5x over x squared minus 6 over x squared. So basically, of this rational function, the degree of the numerator and denominator, both of them 2, right? So I divide each term on the numerator and denominator by x squared.
Okay.
Which simplifies to be 1 minus 4 over x squared over 1 plus 5 over x minus 6x squared. And you can see as x goes to positive or negative infinity, the value will be 1 minus 0 over 1 plus 0 minus 0.
Okay.
That's how we get that one.
Mm.
Okay?
Yeah.
So one of you please mute your microphone, please. So if the degree on the top is less than, the horizontal asymptote is 0. If they are equal, then the horizontal asymptote will be leading coefficient over leading coefficient. But don't forget, you need to write this guy here. It's a horizontal line. It is a horizontal line. Okay, y equals something. Now, what happens if the degree on the top is greater than the degree at the bottom? Then there will be no horizontal asymptote. Okay, there will be no horizontal asymptote. Now we will talk about this a bit later, maybe a bit toward the end. That will be a bit toward the end. We will have the cases when degree on the top is exactly one more degree at the bottom. Then we will have something called slant asymptote. Okay, but before we go there, we will do some examples further, but let's do the vertical asymptote first. Let R star X be the simplified version of Rx. Then the vertical asymptote is given by x equals to the 0 of R star X. Thomas, I don't get you. Don't worry. That's why we need example. Let's take a look on our example 1 again. Our example 1, we have Rx equals to, let me factor them right away. The top one becomes x plus 2, x minus 2. The bottom we get x plus 6, x minus 1. Can I simplify this?
No.
No. So this is the simplest, right? This is the simplest. Now, once it is the simplest, then we can read the vertical asymptote from here. That will be x equals to the 0 of the denominator, x equals to negative 6, and x equals to 1. That's the vertical asymptote. Okay, now let's see. This rational function is actually this graph here. This graph here. Notice that the vertical asymptote is x equals to negative 6. X equals to negative 6. and x equals to 1. You see that?
Mm-hmm.
Okay. Now that's where we basically look at the vertical asymptotes from the 0 of the denominator from the simplified version of the rational function. I think if you look at other textbook, I am basically the only one who introduced this idea of simplified version. But why do I want to introduce this? Because of the following. Let's take a look on example 2. On example 2, we have our, let Rx be, that's x squared minus 4 over x squared plus 5x plus 6, which is equals to x plus 2, x minus 2 over x plus 2, x plus 3. Is it right? I factor them. And in the past, we usually say this is equal to x minus 2 over x plus 3. Is it right? We cancel the x plus 2. But that's not totally true. There's a little difference between the function on the right-hand side here with the function on the left-hand side. There's slight difference. Now, what's the difference? The difference is on the domain. What is the domain on the left-hand side?
-2 and 3. -2
All
and
real
negative.
number except negative 2 and negative 3, right? How about the domain on the right-hand side?
Only -3.
All real number except.
Oh, sorry.
All real number except negative 3. Okay, so what happened is this. They have difference in the domain. When you plug in negative 2 to the left-hand side, it will be undefined. But when you plug in negative 2 on the right-hand side, you will get a number. Okay, so I need to say that the green function is equal to the yellow function only if x is not equal to negative 2. Okay, the graph on the left-hand side is equal to the graph on the right-hand side everywhere except x equals to except when x equals to negative 2. Now, what happens if x equals to negative 2? We know it should be undefined. Okay, now the green one here is the Rx. That's our Rx. Now, the yellow one is what I call R star x. This is our R star x. Okay, that's the simplified version. That's the simplified version. Now, then, what is the vertical asymptote of this function? The vertical asymptote of this Rx.
1.
The vertical asymptote, not horizontal asymptote. Vertical asymptote of this rational function is equal to, is given by x equals to the 0 of the denominator of R star, the simplified one.
-3.
X equals to -3 is the vertical asymptote. Okay. Now, let me say this. I would write that as a big note. A note. when we graph Rx, the rational function, we will first graph R star X, then do adjustment. Okay, so basically if you want to find the vertical asymptote here, that will be the same to the vertical asymptote here. Okay, in fact you can see that the Y-intercept here is the same to the Y-intercept here. The X-intercept here is the same to the X-intercept here. Okay, the domain here will be the same to the domain here, except at this one point, except at the part that they cancel. But everything else, they are the same. That's why.
Oh, so, sorry. So at the -2, that's where you're going to have an extra value at the horizontal asymptote, right?
Extra value of horizontal asymptote?
I made a mistake how I was saying. So that's why the horizontal asymptote can have a point where the graph actually touches it, right? Because
no, that's actually not the reason. No, that's not. No, that's not. That's what I want to explain now. What is the difference between the green graph and the yellow graph? Okay, now let's go to my graphing software. I need to change this guy here. Becomes plus. Divided by x squared plus 5x plus 6. Now, this is what the graph looks like. Okay, this is what the graph of Rx look like. Let me copy paste this into our notes. Copy paste this into our notes. Now I want you to see the following, that this graph here is actually the same graph to our R star X. This is the graph for Rx, which is x squared minus 4 over x squared plus 5x plus 6. Now this graph is the same to R star X, which is x minus 2 over x plus 3, when x is not equals to -2. When x is not equal to -2. Okay, now let's see. When x equals to -2, what happened to this graph? When x equals to -2, what happened to this graph? Do you see this thing here? There's something jumping.
Oh, cups.
No, you don't call that cups.
Oh.
You call that hole.
Oh.
Okay, there's a hole there. There's a hole there. There's a hole there. Okay, so the graph of Rx and the graph of R star X are actually the same graph, except at that one point. At that one point, when x equals to -2, it becomes undefined. Okay, now let's go back to my graphing software. Now notice that this is the graph for x squared minus 4 over x squared plus 5x plus 6, and we see a hole here. Are you with me? Are you with me?
Yeah.
Okay, now notice that we will get the same graph. We will get the same graph when I do x minus 2 over x plus 3. That's the same graph. But you see, you don't have any hole right now. At x equals to -2, when x equals to -2, you don't have any hole. Okay? That's why the way we graph our rational function, we will graph the simplified version first, and then we insert the hole later on. Okay? This is the Rx. Okay? Now, maybe I put a note here. R star X has no hole here. Okay. Remember I said that the graph of Rx is the same to the graph of R star X. The only difference is at the point associated to the factors that you cancel, one of them have a hole, the others not having a hole. Is it okay?
Mm.
Now, one very common question is here, find the coordinate of the hole. Now notice that x equals to -2 is the one that it is undefined at Rx. Right? I think I should say that x equals to -2 is not in the domain. Is not in the domain of Rx. But it is in the domain, x equals to -2 is in the domain of R star X. So we will use this x equals to -2, plug that into R star X. So the coordinate of the hole now, is located at -2, -4. Let me erase this so that you can see it better. See the coordinate of the hole here? That's -2, -4. Okay? -2, -4. That's how we find the whole of a rational function. Now let's apply this idea. Let's apply this idea to another question. Let's say, for example, I have Rx equals to 2x squared minus 3x plus 2 over x squared minus 4. What's the domain? Oh, let me factor this first. This is 2x and x minus 4, I'm sorry, minus 2 plus 1 over x plus 2, x minus 2. Therefore, this is equal to 2x plus 1 over x plus 2 as long as if x not equal to 2, it is undefined if x equals to 2. Okay, so what is the domain?
All real numbers except 2 and -2.
Except 2 and -2. All real numbers except 2 and -2. How about the Y-intercept?
-half. No,
I'm sorry. I think hold on. I make something wrong here. It should be minus here.
Oh.
Yeah, it should be minus there. That's how I get that factor. Okay, so it will be 0.1/2. And then the X-intercept will be, you can just look at the simplified version. The X-intercept will be -1/2 over 0. Okay, it will be undefined at 2. It will be undefined at 2. That's why I have to cross this out. You don't even need to mention it though. Okay, now then how about the horizontal asymptote?
Do we use the simplified R star? Or?
Let's see. If I use R star, what is the horizontal asymptote?
Two. 1.
Hmm?
2. It's 2.
2 over 1, right?
Yeah.
Now, if I use the original rational function,
Oh, it's the same thing?
the same thing.
Yeah.
Okay, it will be the same thing. Remember that the graphs are exactly the same, exactly at holes.
Oh.
Except at holes. Okay, how about the vertical asymptote?
Only a -2.
X equals -2.
Actually, it was
Okay,
-2.
now because we have some canceling there, so I can ask that question actually. Find the coordinate of the hole. Then you will put R star 2. Basically, you put 2 on the simplified version. Okay, let's see if we try to sketch the graph. Let me do it here. Let's say if I sketch the graph. Hold on, shouldn't it be -2? What should be -2 for the R star 2? Oh, the 2 that I use here, is from the undefined version. You see, it is undefined for R, but it is defined for R star. When I plug in -2, to either one of them, it will be undefined. Okay, let's go back. Horizontal asymptote will be y equals to 2. Let's say this is my y equals to 2. Vertical asymptote x equals to -2. Let's say this is my x equals to -2. Y-intercept 0.1/2, 0.1/2 approximately here. And X-intercept is -1/2, approximately here. And then the hole is located at 2,1.25. So this is the hole. So my graph later on will be, see, I come from horizontal asymptote, right? And then when I go to the left, I have a hole. I have a Y-intercept to pass. I have an X-intercept to pass. And then I go down. And from the left-hand side, I will start from horizontal asymptote, of course. Okay. And then you will see we actually go up. Okay, we will go up. Now, you can think in two different ways to know why we go up, why not going down. The first way is to imagine if it goes down. Imagine if I come from this horizontal asymptote here, and then I need to go to vertical asymptote, right? I need to go down. Are you with me? I need to either go up or go down. But suppose I go down, what's wrong with this? Okay, what's wrong is I should have extra X-intercept here. You see that? I should have extra X-intercept here, which I don't, right? According to my computation, I should not have any X-intercept there. I have only X-intercept -1/2, not here. Okay, now that's the first reason we know that the graph comes from horizontal asymptotes and goes to positive infinity at the vertical asymptote. Another reason, which I believe a better reason, is when you do sine graph. When you do sine graph, you will see the critical numbers are -2, -1/2, +2. Will be undefined here, 0 here, and you will see this is positive, positive, negative, positive. Okay, so between -infinity to -2, it should be above x-axis. Between -infinity to +2, it should be above x-axis. Now, if your graph were like from horizontal asymptote and going down, then you violate, there's some part to the left of x equals to -2, you get negative value, which is not supposed to. Okay, So one way to know if it is above or below x-axis, you do the sine graph. I hope now you understand why in your test one, I emphasize so much about doing your sine graph correctly, because you will use it again and again. Okay, and we use it again and again. Things that actually make me upset is sometimes I teach the student one thing, they don't want to learn it the right way, and then later on when that topic comes again, they suddenly, what's that? When did you do that? I forgot. I never see that. You know, okay, because they never really do it, put their hearts in doing it right. I hope you listen to me. Okay, that's for this one here. We end up graphing it already. Now, the last part, what happened if the degree on the top is one more than the degree at the bottom? Let's say, for example, we let Rx equals to, let me do 2x cubed plus 5x. You know what? No. Change it. Make it easier. 2x squared plus 5x minus 4 over, let's say, x plus 2. I want the top to be factorable. How do I do that? Let's change it. Let's change the question. Instead of minus 4, make it plus 2. Nah, not plus 2. Maybe minus something. Minus 3. So I just try to make it factorable. 2x plus 1, x minus 3 over x plus 2. Now, because nothing cancels, then we know there's no whole. Okay, nothing cancels, so there's no whole. How about the domain? Hello?
All real number except -2.
That's right. Or the domain is all real number except -2. How about the Y-intercept?
-3/2.
0, -3 over 2. Again and again.
Sorry.
Hey, it's okay you do it here. Just don't do it in the test.
Okay.
That's half point off there.
Okay.
Okay. Now, it's not only half point off thingy though. The thing is, like, there are so many details you need to put in here. Imagine if you put your Y-intercept at x-axis. That would be a very silly mistake, right?
Yeah.
But that silly mistake happens because we are not paying attention to those little details. Okay, how about x-intercepts? That's negative 1/2, comma 0, and 3, comma 0. So we have two x-intercepts here. How about horizontal asymptote? Horizontal asymptote known because the degree on the top is 2, which is greater than the degree at the bottom, which is what?
1.
Why does that mean there's no asymptote? I don't get it.
No horizontal asymptote. No horizontal asymptote, because if we look back to the rules for horizontal asymptote,
Mhm.
if the degree on the top is more, the third part.
Mhm.
Yeah, if the degree on the top is more than the degree at the bottom, then there's no horizontal asymptote.
Oh, okay, I see.
Okay. Yeah.
Mhm.
Actually, intuitively, if we look at this, if you look at this function here, intuitively, notice that the value on the top will go to infinity faster than the value at the bottom.
Mhm.
Right? Okay.
Yeah.
So infinity, both of them go to infinity, but the top one goes to infinity faster. So eventually, the value of this r, when you go very far to the right, it will be positive infinity.
Right.
Right? It will not get closer to any horizontal constant value.
Mm.
Okay. Now, that's for horizontal asymptote. How about the vertical asymptote?
X equals 2.
Almost right.
2.
That's further away.
The 0 of the denominator. -2.
Oh, negative.
X equals -2. Okay. Now note. If the degree on the top is equal to one more degree at the bottom, like in this case, degree on the top is 2, degree at the bottom is 1, then Rx, the rational function, has what we call oblique asymptote. Sometimes we also call this, in old time, we call that slant asymptote. That's a line, but that's not, that's a line, the line that the graph getting closer to as x goes to positive and negative infinity. But that line is not horizontal. That line is not vertical. Okay, now, so what is the equation of the oblique asymptote or the slant asymptote here? The equation of the slant asymptote is given by y equals to mx plus b. Notice that the degree on the top is one more than the degree at the bottom. So when I actually divide it, I should have linear equation. Okay, let me divide it. 2, 5, -3. You can use long division also though. -2 here, so 2, -4, 1, -2, -5. So the slant asymptote is given by y equals to 2x plus 1 here. That's the 2x plus 1.
What about the -5?
We don't care about it.
Okay.
Yeah, we don't care about it. Now let's try to sketch the graph. I will try to sketch the graph. Now you help me. What's the x-intercept?
-1 and 0, 3 and 0.
-1/2 0, -1/2 0. Let's say this is -1/2 here, and then 3 0. Okay, so -1/2, comma 0, 3 0. How about the y-intercept?
0, comma, -3 2.
0, comma -3/2, so -1.5, right? So here it is. This is -3/2. Now, how about the vertical asymptote?
-2.
-2.
X equals -2.
X equals -2.
So x equals to -2. That's the vertical asymptote. And the slant asymptote is
Y equals 2x plus 1.
y equals to 2x plus 1. Oh, that one is a bit harder to graph. But I try to graph that anyway. The y-intercept is 0, 1. The slope is 2. So the slant asymptote is approximately something like this. Now then, when I sketch the graph later on, you will see it looks like this. It comes from vertical asymptote here. Hold on. Did I do it right?
You just use a sine graph, right?
2x plus 1. It's kind of strange because then it looks like this. And then later on, the one here, it will be like this. Yeah, I just don't like the shape. I was expecting the graph to be like this, you know? Like it's still curvy. Let me erase it. It's still curved, but not like tilted this way. It's not like tilted that way. Not like this. Okay, but let's take a look on the actual graph. Give me a couple more minutes just to show you this graph here. Y equals to, what do I have on the top? 2x squared plus 5x minus 3 divided by x plus 2.
Yeah.
Ah, I get the wrong information from one of you. -3. Duh.
That was me. Sorry.
But hold on.
But
What do we get it right though here? Did I type anything wrong? Ah, this is -5. Duh. Who factored it? It should be like this. It should be. No wonder I get it wrong. Okay. So I have to fix it. I have to fix this badly. This is really bad. Okay, so this is positive 1/2 here. So I have to erase this part. If I didn't check that, I will not get it right. No, it's not there. It's not here. Oops. So this is my -3 here, and I have a positive 1/2. So yeah, the graph's supposed to look like this. See, I know something was wrong. So it's like this basically. So the graph looks like this, kind of. Okay, where am I? Oh, I need to show you this. I was talking about it. This is what it looks like. I fixed it already. The one that earlier, the mistake I make up here, I already fixed it. Please fix yours also. Okay, but then the graph's supposed to look like this here. That's what the graph's supposed to look like. Okay, now I only do 2 or 3 graphing examples from here. That's why I need you to try doing the problems that I suggest to prepare you for your test. Okay, and for this 4.7, the suggested homework from your textbook will be, let me see, suggested homework from your textbook 4.7 will be, let's see, most of them are on the easy side. Number 39, 41, 43. Yeah, answer the questions that I asked you to do. Also, maybe number 45 and 45. It's like the question you need to answer are the domain, the range, X-intercept. I'm sorry, domain, X-intercept, Y-intercept, horizontal asymptote, vertical asymptote, slant asymptote, if any, hole, if any. Okay? Yeah. On Tuesday next week, we will do 1 or 2 more problems. But I prefer you asking me questions though. Okay then. See you then on Tuesday.
Can
Yeah.
I ask you a question?
Uh-huh.
You didn't really. I just didn't understand how the horizontal asymptote can be crossed. I thought